Hello, good evening, everyone. Am I audible?
Yes, sir, you're audible.
Good evening, sir.
Yeah. So,
Sir, today we are discussing questions also.
uh, for this too,
Yes, sir.
haven't prepared anything for this too. Uh, I hope the question idea is similar as the quiz one. So, it is you can deal with that. Maybe I'll just walk into the concepts uh, once again to let you know what kind of questions you can expect. Uh, we'll do look into in that way. Okay.
Okay, sir.
Okay. So shall I start with the concept? So,
Yes, sir.
Yes, sir.
in a minute.
So I have one doubt in week 7 practice assignment.
Yes, yes, give me a minute. Yes, yes. Oh, what should I?
So I have actually doubt in week 7 practice assignment question 9.
It's RNN kind of system, right?
Yes, like it was
Common
told
data.
to, yeah, it was like told to take the like get the output, but there were some random things. If you can explain it.
Okay, so this is about generating random numbers, right?
Yeah. So how we will know that what it will generate randomly?
Yeah, yeah. So these questions cannot be solved without using the compiler or the code thing. You have to run this to find the answer for this. So this is kind of a practical question. We need not be asking quizzes. Okay,
Okay,
this kind of
fine, sir.
questions won't be in
Yeah,
quizzes.
fine, sir, fine, sir.
Okay.
Sir,
Yes.
there is no mark for quiz 2.
Yeah, so I have said we haven't prepared questions like that. So I'll just go through the concepts. Since this is the first time, we haven't got enough time to prepare questions for mark. So that's why. Um, okay, but I'll go give you an idea of what kind of questions you can expect. So you can read upon like that. Okay. So
So it
I
is.
think uh,
So it would be better if you like summarize the concept from week 5 to week 8. It would be
yes,
helpful for us.
yes, yes, that's what I'm going to do. Right.
Sir, is the syllabus from week 1 to week 8 or week 5 to week 8?
Week 1 to 8, you will have like a very small amount of questions. Uh, so you can expect 4 to 5 questions from week 1 to 4, and then you will have similar kind of like higher weightage will be with the for the week 5 to 8, but week 1 to 4 will have like a lower weightage, just the basic
Sir,
things kind of thing.
sir, this time why did they change like the week of like number of weeks for the quiz too? Also because sir, the quiz is not a mock quiz is not there for us. So it is a little difficult to know like what kind of questions to expect and that too from Like,
Week 1 to 4, you can expect the same kind of questions that were asked in week quiz 1, right? You can expect similar questions. So it's just like, it won't be very hard. It's just the basics of thoughts and things like that. Okay. So whatever you have studied for quiz 2, you can maybe take a quick look at the quiz marks and quiz 1 question paper to get an idea. Similar kind of questions will be on the similar lines. Okay.
Okay, so we can say like backprop the questions and those type of questions we should repeat.
Yeah, you can. So totally, so the weightage is like that. Week 1 to 4 has a 1 point weightage, and similarly, this each week has one point weightage. So if your total marks is 5, you will have 1 mark from week 1 to 4, and 1 marks from each of these weeks. The weightage will be like that. So you can get 80% of the questions from week 5 to 8, or 20% questions from week 1 to 4. Okay.
Okay, sir. So, sir, will you be giving practice questions and or solving practice questions in this session also?
Uh, that's what I said. So I haven't prepared the practice questions, but I'll give you an idea of what kind of questions might come. So I think last time I gave you an idea of what kind of questions will come, like the parameter estimation, this kind of idea I gave, right? So similarly, I'll be giving along those lines also. I think last time also we were not able to discuss the marks because
Sir,
marks were
screen is
released
not
yesterday.
visible.
Screen is not
Sir,
visible.
yes, sir. It's live.
So this is happened last time also. Is it visible now? Are they able to finish that?
Yes, sir. Now visible.
Can you see my screen? What screen are you seeing now?
Nothing, freeze.
They'll join from the other person. Then also.
Sir, can I ask a question meanwhile?
Yes.
Sir, I wrote in the group about NPP results. So, anytime, is there a idea about when that can come, or it will come around end sense?
We'll release the NPPT result this weekend. So it is almost ready. So give me a minute. So it's so since it had some manual evaluation parts, that's why it took time. So what we have done is that let me join to the other. Yeah, am I audible, right? Yes.
Yes, sir.
What we have done is that, so since there were many submissions, we had to go through the notebooks to find whether the uh, implementation, so there were marks given for different implementation choices, right? So the one to find the scratch model and the fine-tuned model. So these kind of things were there. So what we have done this time is we have used LLMs to actually look into your notebooks to get an idea about what are the things that are how what kind of implementation you have did in that. So we extracted the metadata, like kind of the details about your notebook, using which we have provided you the scores. So what we found also in the most of the submission is that most people have not made their Tractivo data sets public. So from the notebooks, we see that they have used Tractivo and they have submitted the spaces and the Tractivo dataset link, but the Tractivo dataset link is not public. So because of that, we had to manually check the spaces for the log. The spaces by default usually will be public, but not the data sets, which you have to make public. Uh, Around half of the students have made it correctly. We were able to extract the logs, but for the other people, we are currently looking into that by manually checking the spaces. That's what it is taking time. So by this weekend, that could be ready. After that, we'll release the results with the marks. So since LLM evaluation has been done on your notebooks, we after releasing this, we'll also release a discrepancy form. Those who submit the discrepancy form saying that evaluation is not correct, you can fill that and we'll manually look into the notebook and provide you the necessary mark. Okay.
So like how to check
Mhm.
the dataset is public or not, if you can tell.
Try opening the dataset URL in an incognito window. If you haven't logged in, it won't be available. It won't be showing up there. I think I have mentioned it in the form also. If it is not
Sir,
showing up, you have to make it public. Yes.
sir, one request for next MPP or from next term. Could you please make one video for how we can go with login and how we can make public all these things so we can get the idea before doing the NPP.
Okay. Okay.
Like
Uh, This thing
for
is not an issue since we'll be also doing manual checks. If you have any discrepancies, we'll be doing manual checks, so we don't have to worry about that. Okay.
okay, sir. Actually, this was the first term of this course, so we need some guidance.
Yeah, yeah. Yeah. So let me show you. I think let me share my screen. I'll maybe quickly show how you can check your data set is public or not. That is very trivial thing only.
So I have one. So can I show something?
The screen visible.
Yes, it's visible.
So you go here. You can see whether the data set is public or private here. See now this data set is private. You can see that, right? You can go to the settings and make public. That's it. When you click that, this
Okay,
data will become public, and now you can see the private tag is not there.
So actually, I
Okay.
in the dataset card I do not have anything, but in the files and version there are many things.
The data set card will appear only when you make it public.
Okay, so in the
Okay.
files and version there is the data, but this type of thing is not there. Yeah,
That's
here
what
the
I'm
things are there.
saying. When when you make it public only, it will show the data set viewer and all. In that case, we won't be able to get the actual data from your thing. The files and versions will be visible to you only because the data set is private. Once you make it public, we'll be also anyone can see the files and data. Right?
So
Okay.
can I show you something like I have this problem in this?
Yeah.
So I am sharing the screen. If you can, uh,
Sir, I
is the
have a
screen visible?
request. Sir,
Yeah.
can we please discuss about the upcoming quiz because I'm sure it will take a lot of time.
So it's
Yeah.
showing
Yeah.
like
Sure.
these things. So it shows like something this. Yeah, something like this it shows.
This is fine. I think currently this is public, right? So that is fine. You don't have to worry
So
about
but
it.
sir, like your dataset doesn't shows like me. Like mine is like I can't see anything over here, but your the datas are over there. I don't know how to
Go to
do this.
Data Studio.
Sir, can we please first discuss quiz to Shubham, if I may please
yes, sir,
discuss,
please.
Yeah. Yeah.
Okay,
So
okay,
that
fine,
would be
fine.
better,
because
right?
we also have doubt in this, but I think if we can please discuss after quiz to.
Yeah.
Oh, mm, yeah. Screen again. So you don't have to worry about that now. So we will be manually checking. I was just going to explain that. For now, it is fine. Okay, don't worry about that. We'll be taking care, and you'll be also having a discrepancy form, so don't worry about it. So, okay, week 5, what are the concepts there? I think it will be better if we go to the slides and okay. So, where are the five optimization techniques are there, right? So the different uh, things are there. These are the gradient descent variants. Um, I think it's also, from the exam point of view, we are going into there. So these are the basic concepts. What is convex, concave, the idea of convex functions. Deep learning functions might not be convex, right? So that's why we need different mechanisms. There might be saddle points. How do we go about it? So that's how the ideas. Okay. Mm, okay. So now let's go into the different gradient descent algorithms. The basic idea of the gradient descent is you make an X. So this comes from the Taylor's expansion, how we do the gradient descent, right? So basically, we are trying to approximate the function and we are doing the updates. So now this is the gradient main equation for the simple equation algorithm, t plus 1. This is the gradient, right? So this is basically the definition of that. So now, what are the different variants we have in this? Right? And how do we do batch gradient descent? It's just we sum over all the variables. So gradient descent kind of questions can be asked. You will be given the values, x values, and the learning rate parameters. So you might be asked to compute this. The next iteration, after 2 iterations, what will be the value? Those kind of questions might be asked. Batch kind of questions can be also asked. So here, so 2, 3 data points will be given to you. So you have to approximate everything, like sum up all the gradients to do that, right? Okay, yeah. So now this is the yeah. So we do stochastic gradient descent because sometimes the whole data set might not be. I'm not sure where this autocomplete is helpful or not. Kind of feeling like interrupting me. Okay, fine. Okay, yeah. So now we also have the stochastic gradient descent and mini-batch gradient descent. So So there will be variable, like the variability in the stochastic gradient descent, where the gradient descent algorithm will be smooth, but we might not be able to do the original gradient descent because of the batch size. So we go with the mini batch gradient descent. So in the mini batch gradient descent algorithm, we can uh, do it faster and also progress our gradients forward. So when doing mini batch gradient descent, you have this randomness that is coming. How do we avoid that? So what are the different ways that we can improve that? One way is the learning rate scheduling, because since we are doing the mini batch gradient descent, sometimes there are different things that we will do with the learning rate scheduling. One is this we first initial value will be there. What is the initial value that we have to set? Sometimes this is hyperparameter, so we kind of set it in an optimal way, not too big and not too small. And then sometimes we also use learning rate decay because as we go into near the local minima, it might be very small. The minima might be very small, and the steps we are taking might be too large. So as we proceed, we might want to like slow down a little bit or to find the actual minima. Otherwise, we might be skipping over the minima too often. So something like this that might happen. So you might start here. So your learning rate might be high initially. So you jump here and you jump here, and sometimes you might jump to and forth with which will take a lot of time to reach the local minima. So you take a higher step and take a lower step. So reduce the step size to kind of achieve the local minimum uh, in a shorter amount of time. So that's where decay helps. So these methods, these three methods are the hyperparameter kind of things that we can schedule the things. So the decay and the um, warm up is there. So warm up helps in kind of identifying the first thing. So how warm up goes is we kind of start with the higher learning rate. We kind of increase the learning rate for the first few times and then kind of reduce it. So that is also the technique that has been used in there. And then we also have the other accelerated optimization techniques. So the accelerated optimization techniques are like uh, momentum based acceleration techniques will be there. So we use another technique. In momentum, we also use the velocity. So if the gradient keeps to be in the same direction, we use a momentum term to call that. So to increase the speed of the gradient descent. So how fast we go. Instead of taking constant steps or steps based on only the current gradient, we also use the idea of the previous gradients. So if we are continuously moving in the same direction, it's kind of our velocity is increasing in the sense. So we kind of can take larger steps at that time to roll down faster. So it's just like how a ball kind of accelerates when it goes downhill. So we can easily faster reach the local minima. So that idea will be there.
So
In that sense
what
also, you will be
hyperparameters are you talking about? So if you can repeat that,
not
hyperparameters.
hyperparameters in learning rate scheduling are these three. These are the basic learning rate scheduling hyperparameters. Initial value, the decay, how we are setting it up. The decay will be a function of uh, learning rate with the time steps. So can be 1 by t. That's a perfectly good decay function. Warm up will be also some kind of function which depends upon the initial value and the time step. So as time step grows, how to change the learning rate. So these are very constant learning rate scheduling, which depends upon the time step. Okay, but the other methods, accelerated methods, here these accelerated methods don't not only rely on the time step, also kind of a function of the gradients like that, right? So this gradient kind of accumulates the velocity and you go, right? Uh, this next row acceleration is not discussed here. Okay, next row acceleration is kind of not discussed much in here. So I think we may not go there. So it's kind of a look ahead thing. Okay, so I think we don't have to go over that. But next row acceleration is like you also check with the next gradient step, kind of that. So we don't have to go over that. So there are momentum based and there are adaptive methods. Adaptive methods uses the history of gradients, kind of accumulated history of gradients. Velocity is a function of accumulated gradients, kind of that. Okay. which also have the hyperparameter beta to control how the velocity affects the thing. You have the beta also, right? This is also hyperparameter in the uh, momentum-based methods, right? So, regarding the problems that you can expect, the equations for how you can compute the momentum-based things or the uh, error grades will be given you. So, how these kind of equations will be given to you. You need not memorize this. The problems will be based on uh, what is the next step or something like that, right? What are the momentum values in the next step? How the momentum goes. So that you have to be aware of.
So graph based questions would be there, like for the graph based things.
Uh, Graph-based question in the sense, here, this kind of things.
Yeah, this kind of things.
Yeah, this kind of things will be kind of comparison type questions. So, um, uh, give a simple idea. So, yeah, so these two things are there, right? Comparison. So, given that momentum is being used, you kind of can you guess which is using momentum based thing? So when you use momentum based things, you will see the oscillations kind of reduce, right? So those kind of questions might come. So you might have to be compare different things, which kind of thing. Okay, and this one, yeah, yes. So okay, so regarding this one, you see this, right? How the velocity is being updated over here. So this velocity curve, this kind of relationships are there. How this is being used, right? So these kind of formulas will be given to you, and you will be asked to find the uh, values, any of these values at some time steps. So you can expect those kind of questions from this. Okay, so given the initial values, after certain time steps, you might be asked to compute the resulting value, something like that.
Sir, can we solve
Those are
one
the
question for the above?
okay.
Yes,
Let's
here. Yes, sir.
yeah. Let's take something like this for an example, right? Uh, yes. So let's say computing uh, velocity at time step, right? Okay. So now initial velocity is given, the beta, the other parameters are the beta, right? Okay. And the gradient function we need sometime we need the gradient of this also. Let's assume x is f of x square, something like that. So the gradient will be, so if f is equal to x square, then what will be f grad? Grad f will be this. So now let's say that x is x at time 0 is equal to something like this, and we have this. So how do we compute the velocity at time step? Um,
For simple momentum, we don't have this 1 minus beta term. No?
uh, yes, yes. So we can just use this beta. Beta. Okay, I don't
Yeah.
know. No, no,
Your
no,
formula,
no, no.
Bella.
Yes. Okay, okay. So this is just the radius. Yeah, right. Yeah, according to this equation, and x plus one is this is the eta over here. So the earning rate also I have to fix. We'll fix that. Okay. Okay. So in this case, think now it is being made by full. Let's verify this also. Okay, beta times it is 0, so it's 0. Gradient will be 2x, it is 20, and we are updating, so the value will become 8. So this is how it works.
Formula for the velocity will be given level. So we just have to
Yeah, yeah,
uh,
yeah, yeah.
only the update formula we need to know. Like current step is equal to previous plus eta times the gradient. Only this we need to understand. All
Yes, yes.
the whatever
Because there are like different
add a grad
ways
or
in which
RMS drop,
you
we
can
change
define
the
the
velocity, we change the
yes, yes,
eta, all the formulas will be given.
yes. How the other parameters are changed will be given. This is the
Oh,
basic thing that kind of will be you will be having in everything, right?
yeah, this is the basic update rule.
Yeah. So
Okay, only
these kind
this
of
we have to.
equations will be given to you, and you will be asked to compute these kind of certain values, maybe value at time step 2 and something like that. That's how the initial values setup will be given to you. Okay. So you can expect these kind of questions based upon the equations like this. Okay. This is for this unit. Mathematics, if you think about a problem-based question, these equations will be given to you, and you might be asked to uh, compute some value at some point of time. Right? Other than
Yeah,
that, you can go
here
to
we have
what is the difference between the
we have two
sorry.
methods. Right? One is to manipulate the gradient with the help of the velocity formula. The other one is to manipulate the eta with respect to with help of beta. You divide the eta so that it reduces or increases. Correct. Only
Yes.
two ways we can manipulate the
Yeah, you have various
equation.
different options of manipulating those things, right?
Hmm. I
Yeah.
remember only
So those
two.
kind of things will be given to you.
Okay.
So regarding the mathematical questions that you can expect from this unit, these are the types of questions that you can take. Other than that, it will be concept based. As I said, you have to remember what is the important change or differentiating feature of each of these names, right? So those things you have to what is the something that is individual about that things, so that you can also answer the theoretical questions regarding this unit. Because sometimes the questions might be uh, what is RMS problem doing, and this kind of options will be there. So you want to be able to select this important points about the uh, particular algorithm. So you kind of want to map those also that. Learn the intuition behind every algorithm, the idea behind every algorithm, that is important. And also other than that, the mathematical things, you just have to know about what are the different terms and how the next statements proceed. We will be giving you the equations. You just have to map the values into the things to compute the outputs. So that part will be kind of easy in this. Okay. And I think there was something about uh, uh, how what this regularization, what is the effect of regularization and how it works, or I think you can clear like this.
Lagrangian regularization and projection. Are you saying about that?
Yeah, where was it? Was it before
Constraints.
or later? I think it is initially, right? Yes, yes. So these are what is rate decay and things like this. So it's like adding L1 and L2 penalty. Rate decay is adding L2 penalty with that, and adding L1 penalty will be the uh, will give you something that it's like setting also the constraints on the rates. So that is the idea. The constrained optimization algorithm. So using the Lagrangian, we can also minimize the weights according to it. So So the idea is we want to minimize the loss and also minimize the weights for which the loss is happening. This becomes a constrained optimization problem. We transform that constrained optimization problem into a single unconstrained optimization problem with this Lagrangian, which is kind of equivalent to adding these weights to the uh, adding these penalties to the weights. It kind of makes sense like that. So that's why we rewrite this adding penalty is kind of a constrained optimization problem, similar to constrained optimization problem. Okay, those kind of details you might want to remember about it. I think this is as much as you want to know about week 5. Anything else? Any doubts or if you have anything? Okay, I think and then we want to the week 6.
Sir, what kind of question can we expect on programming side, coding side from week 5?
In week 5, there is not much programming is involved, right? So I guess there will be very less programming questions because it's the concepts that are important. Other than programming, it's just the definition of these optimizers. Basically, these names are the same as uh, the ones that is found in the libraries also. Libraries also have the same names. So just remembering the name is self is fine. Okay. Um, so this is about generative modeling. It's kind of different ideas. So this is about missing value finding and all.
Sir, like this 2x2 grid question can come to physically find the adjoint probability like this.
Yes, you can expect that. So if these values are given to you with the observations, and we can this kind of questions you can expect.
Okay, okay.
Right? So this is about conditional probability. Given the observation, you can predict the uh, missing value. Kind of. That is one thing. That and okay. Okay. So these are the difference between two different ways of model. So one is the generative classifiers and the discriminative. So discriminative classifiers directly learn P of y given x, but generative classifiers learns models this thing and this thing it can generate data. So it can actually generate the y values and using this model, but because by getting this by generating the data, it kind of uh, can also predict this one. So that is the idea. So it has a model of the uh, underlying data distribution. With that, it has each one, and based upon that, with that model, it estimates the probability of it belonging to that. For example, naive Bayes is a very good example for this generative thing because while training for the naive Bayes, you actually model the P of y also using you actually find the means and the variables. You model this one. After you model this one, you kind of predict the y. What is the probability of y? And then with that, you decide. with the one that having the maximum probability. So that's how the generative classifier works. The discriminative classifier directly models the P of X, P of Y. For example, this regression. So whatever you learn, the output is directly P of Y given X. Because from this one, we for generative, we model this to find what is P of Y given X. That is the difference. So yeah, that's about it. So, from the exam point of view, yeah, how this GANs work, right? This generative adversarial networks. So these actually combine these two things, the generative model and a discriminative model. Both are jointly trained in terms of GAN, right? So what is given is from the random noises input, this generative model is tasked to generate samples from the output, learn this idea, and the discriminative model is tasked to identify whether this generated one is true or differentiate between the to classify the original one and the generated one. Based upon this discriminator's decision loss, generative model will get penalty if the discriminative model is getting more uh, good at discriminating the original and fake. And generative model, the discriminative model will get penalty based upon it is uh, not failing to identify the generative models. So these both are jointly trained in this kind of data, right? Yeah. One more thing about generative model is that uh, this latent space representation of something, right? Uh, so every generative modeling models uses something called as latent space representation, takes in uh, data like this and transforms it into a very lower dimensional data, which kind of captures the whole information about this image. So kind of representation learning. The representation learning is a very separate topic of its own in the deep learning, right? Generative models kind of try to learn that representation that, right? So that is the thing. Yeah. So simplify meaningful concepts is something that we. So for example, uh, when you reduce a dog image to a latent space embedding or some lower dimensional data, each value might have some meaning to it. Maybe changing one value in that vector might change the orientation of the image. So that kind of vector learns a meaningful orientation kind of feature in that. So representation of the orientation is computed as a number. So those kind of meaningful things will be captured by this latent space. Yeah. So how do we get these latent space? So there are different ways to do this. PC is one of the things that actually reduces the dimensionality, but there is a loss associated with that also, right? PCA kind of uh, projects the data so that the variance is maximized. So that is the idea. Using that, it uses eigenvalues to compute that. So these are other different uh, latent space reduction techniques. This matrix factorization and these other things. And in general, we call this encoder kind of models. Whatever transformations that we use that reduces the data to a latent space, we call this encoders. And this latent space sampling. So how do we sample the latent space is something that we get. So in this, so you have this latent space representation, and you kind of in this the decoder model will be there, which is kind of takes in this latent space representation and gives you the uh, the image back, right? So that is the decoder or the generator. So if we kind of add this, like if we create a so this latent space also has its own probability distribution. So if we sample randomly from that distribution, we kind of can generate different images similar to that. So that is the idea. So these two things were like uh, this was used in these models like variational autoencoders and the scans. Variational autoencoders kind of uses this sampling and the encoder decoder architecture to get this thing. So this is kind of a generative model, you can say, but it uses the latent, it makes use of the latent space representation. Here this combines both generative and discriminative models, and the generative part also has this latent space representation. From the calculations or questions point of view, I don't think much of math or problem related questions are here in this. It's mostly concept based. You have to get the idea of this architectures. That's it. So just go through that. Uh, Equations you can uh, don't try to, you need not try to get into detail these equations. Just get an idea of how these work. That is necessary for from the exam point of view. Okay. Just get the idea of what we are trying to do. Don't worry about these equations. Other than that, I don't think you have much math in here. That's basically that's fine. Just go through how the basic concepts of GANs and various non-controllers. Okay, that's about week 8. Week, sorry, week 6. We'll go to week 7 and week. This is about RNN. So here you can expect some questions, like some more math kind of questions, and you also have this data modeling. So right, uh, this tokenization and other concepts will be there. So that is something that you might want to look into. Uh, this is other basic
Sir, can you please take
things
one
of
or two examples from practice assignment for this week, sir?
week 7.
Yes, sir.
This is RMN, uh, this one.
So any question that you think might be relevant for us for history?
Sir, in week 7, I have many doubts in programming questions, sir. How the shape of the output is determined.
Okay, here, this kind of question. How many parameters?
And
Here,
in graded
this
assignment, they
one,
are given, yeah, this only.
this one.
How shape of output
Okay,
and
okay. So
Yes,
for
sir.
that, you have, yeah, yeah. So I think I will go to this one. Yeah, this one. Right. Yeah. Okay. Yeah, this kind of questions also you can expect this shape kind of questions and this parameter kind of questions that you can expect here in this unit. Okay. So let's take this one, the shape question. Okay. So this is their input shape, right? So this input represents a single sequence. So this is the innermost dimension, which is the vector representation of one sample or one time step in a sequence. So this dimension is the innermost dimension. So you have the uh, vector dimension and you have the sequence dimension and you have the batch dimension, right? So this what this represents is that there are uh, 7 sequences, each has 5 sequence length, and each value is of fourth dimension, right? We have to think it like that. So
What is the last one? The 4?
this is the vector dimension. So for example, if you are using words, each word will be represented by some vector, right? Each word will be represented by some, if you are using simple one-part encoding for each word will have some dimension, right? And there
Okay.
are 5
Yes,
words in
sir.
that sentence, and there are 7 such sentences. Okay.
So the middle is the sequence dimension, the 5.
Ah,
Is it the length
yes.
of each sentence?
Yeah, length of the sentence, kind of that. Yes.
Sir, length of the sentence is 4.
No, 5.
Okay, sir. So, sir, what is the vector dimension mean?
Vector dimension means, so each word will be represented by a vector, right? What is the dimension of that vector? You can think it like that.
Sir, can you please explain through one example by taking one word?
So if you are encoding, so let's say the cat is on the mat, right? This one has 6 words. So sequence length is 6. Here it is 6. Each word will be represented by some vector, right? They have to represent that, this kind of this words into some vector, right? Something like this. And this vector, there is some example of one hot encoding, and this vector dimension is 4, right? Here it is 6, but here we are assuming it is 4, something like that. And there are 6 such
That
sentences. Yes.
how is the vector dimension 4?
Vector dimension is the representation of that word in some n-dimensional vector space. It will depend upon the vocabulary or the different embedding methods that we use. There are different tokenization things that we have, right? After tokenization, we encode the word into some vector like this. This is a simple example of one-hot encoding, but modern tokenization methods use different. Uh, you also seen this embedding methods like scriptgram and other things, right? Word embeddings. Each word will be represented by some n-length vector. That is the basic idea.
So the tokenization and the encoding like refer to the same concept type things, like changing the like numerical encoding.
Tokenization is splitting the sentence into parts. Encoding is representing that parts into a vector. Here we have used a simple word-based tokenization, right? Splitting is called tokenization. Representing that units, here everything is word-based and we represent the words as something like this. Tokenization is splitting into chunks. Embedding or encoding is mapping the chunks into the whole set of all the chunks that we have formed is called the vocabulary, right? Here actually
That
the
depends
vocabulary
on
is
the
6.
corpus or vocabulary. That is what is the.
Ah, yes. This,
So that
and
is
sometimes
already
we also form this vector embeddings, which will be kind of not in the size of vocabulary. It will be a much lesser dimension that we learn through the repeated occurrences. Like different models are there, right? Scriptgram, continuous bag of words, glove embeddings are there, and some other embeddings are there, which translates these tokens into some n-dimensional vector.
so how the tokenization is actually performing, because that the words are already split. Like how it is actually
No,
being
no.
done.
Splitting by words is one method for tokenization, but there are more advanced tokenization methods are there, which might split to the suffix, prefix, common suffixes like ing might be a token in that. There are different methods which are not covered as part of this code. Modern methods, one is this byte pair encoding. If you can take a look at that, PPE is one of the very famous, currently most the Berkt and all uses this things. You can take a look at that. You can go through this to get an idea of how BPE works to find these tokens. Right? It starts from individual letters and kind of combines most commonly occurring letters together to form higher level tokens like that. So you can take a look at that. So this is one thing. So you don't worry about those tokenization methods. For this course, the toy examples will be mostly having this word-based tokenization. Right? Simply each word will be considered as token. Because for mathematical toy examples, you will have a very limited set of vocabulary. In that case, word-based tokenization is fine. Okay. So, do you get now what these values are?
Yes, sir.
Sir, sir, the vector dimension is the size of the vector. In this case, it
Yes,
is
this
the
one.
okay,
Length of this one. Length
okay,
of this one is the vector dimension. This is the sequence dimension. So here there will be these vectors will be here, right? What is the length? 6. That will be sequence dimension. Here also, here the vector dimension seems to be 7. So we can have that here. Vector dimension we can have 7. And the dash dimension depends upon the number of sentences that will be.
okay,
Kind of that.
okay, sir.
And now let's go into the RNN model. So what are these values? Okay, we'll take a look into that. Input size, hidden size, number of layers, right? So this is very similar to the dense layer, kind of that. Input size, what is the hidden size? How many layers are there? So that is it representing. So with that, this is the input size, which matches with the vector dimension, right? This is the hidden size, which means the output of this RNN, which will be of. So one time when we pass one time step of the sequence, we will get an output dimension of 6 as the vector, right? And that is the idea of this one. And what are we doing over here is that uh, we have RNN and we are passing the mm, yeah. So RNN takes in two things. One is the X and one is the H, the previous H. So initializing. So this is basically initialization to be zeros. The first time step of the hidden thing are set to be 0, and these two things are passed to give you an output of this. Now, what will be the output shape, right? So there is this out and hut chain, right?
So, sorry, H naught, how are we defining the size of H naught?
So what is the size of hutch? Size of hutch is a 6-dimensional vector, right? It is a 6-dimensional vector, right? Hutch is a 6-dimensional vector. The
6
output,
actually is the output size, no, for RNN. Is it the size for
hidden size, hidden size, hidden size. This is hidden size.
Oh, okay, okay, okay.
Okay. Okay. Um, Okay, one more thing to note about this is that this batch first dimension over here, right? Yes. So this is something that you have to be aware of. So when you have batch first equal to false, which means the input over here, for example, yeah, when batch first equal to false, means the batch dimension and sequence dimension will interchange. So by default, in this case, if we are setting this RMN to be this, we are setting batch first equal to false, which means this 5 will be the batch size. Consider as the batch dimension here. This will be the sequence length. So if we are defining this RMN like this, if we are defining the RMN like this, by default, the RMN layer assumes the first dimension to be the sequence length rather than the batch size. Okay. So in this case, actually, this is assumed to be the batch size and this is the sequence length. Batch first is said to be true, then this one will be the batch size. Okay. So since the nothing is defined, we will take the default value. So batch first will be false, means this is the batch dimension. 5 is the batch dimension and 7 is the sequence length.
So number of sentence will become 5.
Yes. Oh,
Oh,
yes. Number of segments is 5.
okay, okay, sir.
Yes.
Batch first is false means then 5 becomes the batch size, no?
Yes. Yes. Yes.
So number of.
Number of sentences is the batch size.
Okay.
Length of the sentence is the sequence length.
Okay.
Okay. Okay. So now we have this. So Hudson. Let's talk about only the Hudson first. What will be the output of this Hudson? So yes. So the Hudson has the dimension of 6, and for each of the uh, input length, sorry, the step size, we will get a 6-dimensional thing. So since the batch, so this is the sequence length, right? So you will have this sequence length. Where is that? Okay, we are taking only the last. This section is the just the last uh, step, right? This is just the last one. So you will for okay, you will have a. This is the batch length. So this will be there. So this batch dimension will be preserved, right? So 5 should be there, and the vector dimension of the hidden size is 6. So 6 should be there, the last dimension. So these two are, this is the correct value, right? And there will be one such thing at the last time step. At the end time step, we will have some one value, and that one value and that size will be preserved. For 5 sentences, you will need to have 5 hidden states at time step n, and the size of the thing is each hidden state is 6. So this one of this is the correct answer for the H. Now we have to choose the correct answer for the out. Okay. So let's see about the out. Hmm, what? So the batch size is 5. That should be preserved. So I think batch size is preserved in all the options. So that is fine. Uh, then okay. For each of this sequences, we need to have each of the output, right? And that is usually the output size is same as the batch this hidden size. Uh, wait. Yes, yes. The output size is same as the hidden size. Okay, so it will be like this. So with this itself, you can determine, with this itself, you can determine, because the sequence length should be preserved in the output. For each time step, you will get one output, right? Like that. So either you have to get uh, outputs at each time step. Sometimes you also have this configuration of just giving the nth time step, right? Uh, Seeing how do we process that one? Yes. So whatever you got as output, this is kind of the equivalent code demonstrating how this RNN works, right? So all layers, each time steps output is concatenated into that. So you need to have 7 values in there. That is the idea. So output will have each output for the values, and hidden still will have this one. So output is like all the hidden states combined together, right? So I think this one. Yes, this one. So hidden state, and there will be this y giving us the output, which is usually the same. It will be usually of the same dimension. That's what we are getting in the output here. So that will have that need to have 7 values from there. So that makes this is the correct answer.
So one question is there, like in the forward pass, we are passing the RNN as x comma h naught. So like actually I want to
Yes,
know that how we are getting the two outputs. Like I'm just confused bit.
this is the h naught is the initial h value. So for example, here you have to pass the initial h value, right? There should be time step 0 where there is the initial h value should be there. That is 0. That's what we are saying here, right?
So the
Initial
size
h
of,
value.
what is the size of it? Like it's basically the
This
156. Yeah,
yes,
it's 15. Okay, understood.
this is that size.
So how is the RNN taking that? Like I want to know that how is the RNN feeding that in that upper code self.rnn is equals to.
Yeah, here. So R1 is this equation, right? So to compute the current heads, you need the previous heads, correct? So the initial value should be something, right?
So like we are passing it as a parameter, right? In that code. Like I want to know that part.
Yes,
That we are allowed to pass it as a parameter in that RNN.
yes. See here, the forward takes in input and heads, the initial heads. Okay,
Okay, understood, sir. Yeah.
this is optional, I think. Yeah, I think when you don't pass, it automatically takes it as 0. I guess is it given here? Uh,
So like we're basically initializing the hidden layer as 6 zeros, like the zero vectors and all.
yes. So that's the idea.
Yeah, understood, sir.
Okay, you can also have random values. Sometimes in encoder decoder architecture, H naught will be the encoded context vector of the initial value for the decoder will be the H naught of the encoder architecture. So the last context vector will be passed as H naught to the decoder. So that gives us flexibility to start with.
So, but if we remember, like in the from week 1 to 4, we were using 4 values in the torch.rand in one, like 4 values. But here we are using 3 values.
4 values, it depends upon what kind of input you have. I think the 4 values that you have saw
CNN, yeah,
is
CNN
for
for
image data, where
yeah.
the batch and the spatial dimension and the channels.
Like the
right?
structure is same for both the cases, right? For three things.
Oh, for 2D CNN, the input should be four-dimensional.
Yeah.
For RMN, the input should be three-dimensional.
Okay. Understood. Yeah. Understood.
It depends upon the network that we are doing, right? For 1D CNN, the input size should be three-dimensional. One is batch size, the spatial single spatial dimension, and the channel dimension.
Yes, sir.
So for sentences, people also have used the 1D CNNs to do classification tasks before the RNNs. So that also has a similar input shape. Okay. Yes. So yeah, so here you can actually see this one. The batch bus is being set to true. So you have to remember that this is there. Okay. Excluding bias. Okay. Exclude bias. So no bias. So how many parameters will be there? So the hidden size is 20. So there will be,
400, I think, and 200. 400 plus 200.
let's see. Oops. So what are the different parameters that we have in RNN? We have W, I, W,
XH.
no, I'm trying to stop the autocomplete. It is giving values according to the previous sequences. Yes. H and H and H. So three things are there, right? This all will be depending upon. Okay. So as I said, the input size is 10. So this matrix will be 10 into 20.
So 10 cross 20 or 20 cross 10?
Both are same rate.
Yeah, but for the from the
It
again
depends
we
upon how you orient the input. If you like transpose, if you orient as a 10 cross 20, you have to adjust the input like that. If you how you specify the input depends upon the orientation. So that is fine. You can always adjust to the position and thing. So if you are like telling this as W, sorry, X, XT, W, T, something like that, you have to, how do we turn off this? I think after a new update, this autocomplete came naturally reduced. This, yeah, I think this one, right?
There was an option to disable when you say
Where?
autocomplete. Yeah, when you say autocomplete in the extensions, there was an option to disable.
Here.
The top. Yes, yes. Autocomplete. Oh, yeah. Disable auto update.
Where? It's this auto update, right?
Auto update only. Auto save, auto come. What is auto come?
No, that is just asking to Copilot. I think this is
Right.
the one that is doing there. This is
Sir,
the
I
one.
think it has
This
been
is the one that
disabled.
is using.
There is a sign coming. I think it
Okay.
is disabled. Oh,
It's still coming.
still coming.
Oh, which extension is this? This is from Copilot only, right? It should be
Try to uninstall Copilot from extensions.
this
So,
Copilot status to seem to be off only,
so
right? It is not turned on. It's off only. Maybe it is- Okay, fine. Let's just or else I'll open plain text editor. Yeah. Okay. Yes. So we have input size and then size P, right? So we have three matrices. So the W XX will be of shape 10 comma 20 or 20 comma 10 doesn't matter. And just say in parameters 10 into 20 because we are ignoring the uh, biases. Okay. And similarly, what about HH?
If bias is there, it's plus 20, no?
Ah, yes, you have to, if bias is there, it will be this thing plus 1, input size plus 1 mm, into 20. Right. Yes,
So we are biased in the
right.
input layer and the output layer. Like output and hidden layer only in the bias are there.
No, this is number of parameters.
Yeah, but we are counting the bias also. So plus one is for bias for like how?
Okay. So W, okay. How it works? Wi times xi, right?
It's yeah.
It's a summation of W times xi. Bias is like some Wi, correct?
Plus
Some
xi into x.
W0. Some W0 will be there, right? This W0 will be there for all of this 20 hidden layers. So there will be 20 neurons in this one, and each one will have some W0, correct?
Yeah, yes.
Now, when you multiply this, basically adding 20 to it. So it's just like you are adding a oneness, you are attaching one to the, you are concatenating one with the input, right? X naught is equal to 1. You can add an one dimension, a dimension to the input, setting its value to 1, which will be exactly same as this.
Okay,
So now X
understood.
naught
Like I
is
was having the like
1.
confused with the calculation, but yeah, it's 220 only. Yeah, 200 plus 20 neurons. Yeah, so same only.
So this is with biases. This is without biases.
So actually, the confusion is
And
like in the input layer we calculate the bias, or the output layer we cancel it. Like I forgot that thing.
no. So it's like the number of biases, how biases work. So this is the equation, right? Wxi plus W naught. W naught is the bias. Okay. For each neuron, W naught is the bias. So it is similar to adding a dimension to the input and making it value 1. So the input dimension increases by 1. Biases are some, you can construct. So assume you have a x1, x2, x3, and you have w1, w1, w2, w3, and you also need a w naught. And now what is the dot product? This one, right?
Okay.
So did you see when we add biases, we are increasing the input dimension by 1 and setting the value to be 1. It's equivalent. That's why I increased the input dimension to 1. You try expanding the dot product of these two, you will get this equation, right?
Yeah,
That's why I expect I now I increase the input dimension to 1, right? That's why I did there also.
yeah, understood.
Okay. So without biases. So this one W H H will be H into H. So 20 into 20. W HY will be, so the output size will be same as the hidden size. So in that case, it will
Sir,
be,
what is the number
yes,
of layers? One.
1, I guess.
Okay.
I I think output layer is being this considered no output, so we can ignore this. There is no output, so we need not have that weights associated with that.
Sir, if
So
it is there, what will be the dimensions?
you just have to add this um, 20 into 20. What is the this will be the output size also.
Okay, sir.
So 20 into 10 will be, or 20.
20 into n, yeah.
Okay. Okay.
Okay. So here you have seen, right? This is the output size. The same as the hidden size. Hmm. Um, so output is basically this output is what we are adding to this output, this hidden layer and h of t minus 1. So output is whatever we are getting output from this RMN is basically the hidden states. Okay, this hidden states. This is at each time step concatenated together is what we are getting from the output. So this RMN by definition of this PyTorch doesn't have that WY matrix at all. If you want a WY, we have to add a linear layer on top of the RMN with the specified output size. Okay, this, this is just the layer. So this layer only represents these two parts. If you want a WY, we add another linear layer on top of this RNN to give you the desired dimension of Y value. So basically the RNN in PyTorch only has these two things. The H is computed in each time step, right? So this value out is concatenation of all the hidden states throughout the RNN execution. This is the last one. Okay. If you want an output, you have to attach a sequential layer with the RNN with the desired output size. The input size will be that. As you see, the RNN don't have the WHY. This layer doesn't have the WHY. If you want to create a network with that output, you have to add a linear layer on top of it. Okay, so as you see, this is how the forward of the RNN is defined in Python. This don't have the output. If you want to have the output, if we are saying there is output means in the sense of Y, we should add a sequential layer with the RNN with the output size. Then only you have those ways. So by this one doesn't have the output uh, at all. So the parameters are just these things. If you want Y, we have to add another linear layer on top of it. So these are the total number of parameters currently in that. So if num layers increase, we if num layers increase, we have to uh, have this times num layers.
Sir, norm layers means the like it will be same structure everywhere, like the same hidden size 20
Yes,
with input size 10 and all.
hidden size will be repeated, kind of stacked.
Only the hidden size or the like, oh yeah, only the hidden size only. Yeah, yeah, understood.
Hidden size, right? Yeah.
Yeah.
It's like creating a dense layer which is recurrent with this number of layers. The hidden size will be 20.
Like changing the
These are the
hidden layer size
parameters.
will create the model to like go away, it will manipulate things, because if we change the hidden size it will compute different things.
Oh, I'm not getting what you're saying.
So like if we like in the first layer, it is the hidden layer is hidden size is 20, and after that I am changing the hidden size from 20 to 12, so it will create a problem obviously.
Here, that option is not there. If you want those kind of things, if you want to change the hidden size at every level, you
Yeah.
have to stack another RNN layer with a different hidden size. Input size will be this one.
Okay, understood.
Okay. If you want to
Sir,
create something complex, you cannot do that in a single RNN class. Here, this will have the same hidden size throughout the layer.
Okay.
sir,
If you
if
want
this
different
is a
hidden,
classification,
yes.
this is a
Sorry.
classification problem of 5 classes.
Yeah, then you
Then
will
the
add
output
a
then the output will be 20 into 5. Plus, if there is a bias, then it will be adding 20, right?
So there are different ways, right? So RNN, this cell can be, for example, in an encoder decoder architecture, there will be a single output Y, which will be computed from the HN. HN will be passed to a linear layer to give you uh, some output size of this one. If you are using a, uh, if you want output at every time step, you will be combining, stacking that RNN linear layer with that. There are two ways in which you can attach the linear layer with this RNN. One is by stacking that with the RNN, use that output every time. Another one is just passing the HN to the linear layer. Right. In any case, the number of parameters in the linear layer is same. Which way you choose to use it, the parameters in the linear layer is same, right? It depends upon the input size and the hidden size. Okay. Did you get that? The parameters are defined by the layer itself. So RNN doesn't define the output size. It only has hidden state. Depending upon your application, you can choose to give outputs at every time step, in which, in that case, you have to create a sequential layer with RNN and a linear layer. So that will give you a sequential output of that. If you want to just pass the final value to the linear layer, then you have to call this one to get the HN and just pass the HN to the linear layer to get some final classification output. Is that clear?
Then what will be the number of parameters? It will differ in
Number
both the
of
cases.
parameters in linear layer will be same, right? So how will you define a linear layer? It does, in both
Yeah,
cases, number of
suppose
parameters is same. A
yeah,
linear layer will have
the
input size and a hidden size.
yeah.
Okay.
So
Yeah. Is it clear?
yes.
So a linear layer, in any case, the layer only has the parameters. So we are into the two ways of implementation. We are just changing what we pass as the input. Like, do you pass only the last time step at the input for the linear layer? Is one choice. Do you pass every time step to the linear layer? Is another choice. But in both cases, the number of parameters in a linear layer just depends upon the input size and the hidden size. Right? Only these two depends to compute the parameters. Okay. Just have to multiply these two things. The biases, you have to add one to the input dimension and multiply. Is that clear?
Yes, sir.
Okay.
So we can like expect similar question from the LSTM and the GT, like the G graded questions and all, for the LSTM and all.
Yeah, you can expect. So what is the difference that you have? Here, you will have two outputs coming out of it. One is the E and the H. These two things that you will get. The hidden size is that, right? So you will have these three. You will have like the H0, and you will have also have option for C0. And the output you will have this concatenated things. This concatenated thing is the let's see. Wait, this is the last hidden state. This is the last cell state, and this concatenated thing is uh, LDH. So sequence first. So by default, it will be sequence first, not batch first. So sequence length and mm, D into so D is bidirectional. That is fine. That's out. What is the hidden output set? So the hidden states are concatenated together. That is the same as that. The only thing is you also have a cell state, final cell state coming in, and initial cell state going in. That is the only difference from the outside, right? Regarding the parameters, it might be a little complicated depending upon the equations, since you have all these things. These weight
This would be
matrix.
given. So like this type of questions like would be given to our, like the paper should be containing this type of questions.
Paper should be containing this type of questions. It can be there. It's basically so the computation is not very complex. As you see, the parameters are just these W and B's, right? The parameters are not doesn't depend upon the activation function or the other things. Only these W's and B's are the parameter. Okay, you just have to know what is the input and the output state here. So if you know the dimension of these W's, you just have to add up the dimension of the W matrices. You don't have to think about any other parameter, any other things here. Just uh, computing the parameters is just knowing the size of the weight matrix. Okay, it depends
Okay.
upon the input size and the hidden size. Okay, in
Sir, can
RNN,
you give one example for
mostly
LSTM?
okay, you have in LSTM also you have the same input size and hidden size, right?
Yes, sir.
So what is the shape of this one? Input into hidden. What is the shape of this one? Input into hidden. Sorry. Uh, wait. Oh no, this one is hidden into hidden. So this is input into hidden. This is hidden into hidden, and this is also input into hidden, hidden into hidden. So basically three times. Let's see, four times. Four times of that of the RNN. So in RNN you have one of these and one of these. Here you have four of these and four of these. So it's basically four times the RNN. These are our H, right? Hidden size into hidden size. These are our input into hidden size. These layers don't have parameters, right? This is just multiplication, addition, and all. Parameters are only these. So this is four times. In GRU, what you have is three times. That's it. This is H into H and this is X into H. Three times that of RNN is the number of parameters in the GRU. Not much complicated now, right?
Yes, sir.
Sir, what do we do in the Hadamard operation, sir? What is that?
Element based multiplication. You multiply corresponding elements instead of doing matrix multiplication. That is a Raman product. Element-wise multiplication. This is another name for element-wise multiplication. In NumPy, if you just multiply two matrices with the star symbol, asterisk symbol, you will get an Raman product. In Python also you can do that. Take two tensors, put some the star symbol, that is this symbol. Mathematically, people use this. In code, you use the asterisk.
Okay, sir. Okay.
Right? So in both of these, all of these three things, the parameters depends upon input size, hidden size, and num layers. If you know how to compute it for R and N, multiply it with 4, you will get the LSTM. Multiply it with 3, you will get the R. That's it. Okay. 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 I think those things are also about the LSTM and all to come here, right? Okay, here, I think this kind of modeling also there. Okay. Yeah, in the I think in the week 8 there were some part about the decoding and also there. So I think we'll also need to look into that. This one.
The encoder and decoder, I think.
No, not about that. Like how do you map things like that? So this is the use of vocabulary and all. This is something that I said, right? This is how you pass the inputs to this one. This kind of questions you can expect. Some kind of vocabulary building kind of questions you can expect. And PPPT also you can expect something. The relevant equations will be given to you, so you don't have to worry about that if that kind of questions
Sir,
is
in this I
asked.
have one doubt, sir. Here
Yes.
in the numerical examples of weights, they are given WHY something, no, sir?
Uh-huh.
Like how output size is same as input size there?
Oh, this okay. The RNN here refers to the whole network, but the RNN here refers to only the RNN layer. So these RNN, this RNN here is this RNN plus a linear layer. Okay.
Oh,
The
okay,
thing
sir.
that they are referring to RNN here is RNN plus linear layer. This RNN will only give you H. It won't give you Y. But for prediction, we also need Y, which is basically a linear layer. Okay.
Okay,
This
sir.
one. The outputs here doesn't refers this output doesn't refers to the Y. This output is the concatenation of all the hatches in every time steps. That's what displayed here. The output that is coming out of the RNN layer is the concatenation. You see this one? Concatenation of outputs, which is the hidden state at each time step. Okay, the output here is not does not refers to the Y here. It refers to time all the hatches. Okay, so you should be careful about this. Here RNN refers to RNN plus linear layer in the Python. The network, the whole network is kind of called like that. Okay, so you should be aware of this distinction. Okay. So when you set the linear layer, you can set the input size of the linear layer to be the hidden size of this RNN and the output size to be the desired output size. Here the output size will be the hidden size because the output is concatenation of all the hidden states. Okay.
Is
Output.
there any use for this output? Whichever is concatenated, is there any use?
If you have to predict like Wy at each time step, you need Wh at each time step, right?
Okay, but it is concatenated all together. So whenever we want, we have to go through the loop and get that.
So it concatenated along a different dimension, not in the like it's not like it is stacked, not concatenated, stacked, which means each thing will be in each state will be in a different index. Each time step will be in one dimension, not concatenated, it is stacked. Stacking is different from concatenation. Concatenation means you join along an existing axis. Stacking will create a new axis. Will add a new dimension. So if the each hidden layer, if each of the hidden layer is some n into m into n, this will be let's take the number of time steps to be capital T. It will be t times m into n. The shape of output will be t times m into n. So basically, it's basically like when you pass this to a linear layer, each time step you can consider as a batch, right? The time step dimension will become the batch dimension. So you pass those batch of hidden states to a linear layer to get a batch of outputs. Okay, at each time steps.
Okay, okay.
Stacking is different from concatenation. Okay, stacking adds a new axis. The kind of yes. Okay. Then these are the LSTM and other things. I think we will just those things. Right. The bidirectional RNN, you have two things. I think in RNN you have a bidirectional parameter also. If bidirectional is said to be true, you will have two times the weight matrices. So you will have a forward weight matrix and a backward weight matrix also. So this number of parameters will be times two. If you have a that bidirectional equal to true, the parameters will affect. Okay? We will have two things, two input and hidden matrices. Okay. Okay. This
Sorry, in blue score, some discrepancy was Pulkit was saying something here. The in the lecture portion, two were used. One is here, and the another one is in the example. So he said he will confirm before the exam which one to use.
which is the one.
Uh, uh, this one, the uh, yeah, and here he has used only the e part, exponential part.
No. He has computed. We have computed this. This is just the BP. So this blue score is the whole thing. This is the BP, brevity penalty. This part is called the BP. That is what we are computing here. BP is the brevity penalty only, and then the blue score is BP times this precisions. This product. Product is there, right? TN, unigram precision, bigram precision. So when k is equal to 2, we take unigram precision and bigram precisions. In k is equal to 3, we also take trigram precisions. Here, but this these also computed. Each of these key values are also computed. It is computed to be 1, and this is also computed to be 1. So that's why it's like kind of exact match. So this example was particularly taken to show that. So since this value is 1, that's why you just get this value as the result. Because this product is 1, so this will be 1, right? In this particular example, this is kind of taken. This is a very particular example to show that why derivative penalty is needed. Okay, even when these are 1, these two sentences are not same, so there should be some penalty given for not predicting the whole sentence. That's what derivative penalty is. This example just shows a special case where these precisions are 1. So in that case, the total blue score will be just the BP, right? That's why these two are being equal. Other than that, the equation is correct only. If you have a mistake in the unigram or bigram precision, then you will have a penalty standard. So assuming here, yes. So here, assume there is C. Okay. Unigram precision will be okay because A is there, A is there, B is there, B is there. Unigram precision is. What about bigram precision? AC is not there. So that is a miss. Like that. So there is one diagram AC and AC is not present in this thing. So you diagram precision will be 0. Okay. Like that. So in that case, the whole blue score will go down. So diagram precision is not matching. Kind of that. So is it clear?
Yes, sir, right. Look that because somewhere we found something different.
Here it is just the VP because these two terms became one. Otherwise, this will also have the effect on the overall blue score.
Sir, are we going to get any question on blue school?
It might get.
Sir, can you throw some light on this perplexity also? How, what is the intuition behind that? Something was taught.
Perplexity, the basic intuition is how confident is the model in predicting the sentence, right? For example, assume that we have a vocabulary size of 5. Okay, we have a vocabulary size of 5. So each output, when you predict the next word, we have a probability distribution over 5 words to choose the next word, right? So we have 5 words. Let's see. So if the probability, so it will be a final softmax layer which predicts the probability of each of the words. Now assume this one is 0.8 and 0.05, 0.05, 0.05, 0.05. Okay, so this is assume this is one kind of prediction that is being made. And another model predicts like this. It predicts 0.3, 0.2, 0.2, 2, let's say how much we have.
One and one.
Right. So now, can you see a difference between these two models?
Yeah, the first model is more confident about the
Yes.
first
So
point.
this one will have less perplexity. This
Okay.
will have more perplexity. Okay. That is the idea. I think it is
If
perplexity is
complexity is
major.
less, the more confident the model is.
Yes. Yeah, lower is the better, right? If perplexity is less, the model is better, which means perplexity is less here. The model is good. It is confident. Confidence is high. It has less perplexity. Confidence is low. It is kind of distributed among all these things, right? So it is not very confident about this answer. Even we might choose this as the correct word, right? But since the model is not confident about this output, as we can see, this is kind of better. This has less perplexity. This has more perplexity. This I hope this gives you a basic intuition on that.
What is
It's
the
basically this one.
relation between the size of the vocabulary? That is what.
Output size would be the size of the vocabulary, right? So each of this thing is a probability for the ith word. So
Okay.
if you are predicting words,
It is
you
uniformly
are actually
distributed.
predicting a probability distribution over your vocabulary, correct?
Okay. Okay.
So usually the final size will be the vocabulary size, right? The final output dimension
Yeah. Yeah.
will be
Yeah.
the size of the vocabulary.
Okay.
So here this P of x given all these things, it is just the probability basically. These things only. These probabilities, and they are just taking the log sum exponential of it, negative log likelihood. It's basically the negative log likelihood is the loss function kind of thing that we use, right? In a softmax layer. It's very same as that. But here we kind of average out the uh, each time steps. Like it's basically the loss function that you use. It's just a very different term saying that. Okay. Hmm. If model is more confident, the loss will be less and the perplexity will be less. Okay. Okay. Anything else?
Sir, the corpus and vocabulary are same thing.
Corpus is the if you have a bunch of documents like with some text paragraphs, that is called the corpus. All the text is called the corpus. Vocabulary refers to the unique words or the unique tokens that you have extracted from the corpus. Vocabulary is the set of tokens, not the whole corpus. Corpus is the all the text document. Vocabulary is the unique set of tokens that you have extracted from the corpus.
Okay, okay.
Okay. Uh, Regarding this, I don't see any issues with this formula. I hope that would be okay. Okay. And then something there is beam search is there, right? How do we do beam search? This could be also a question you get, right? Uh, Based upon the probabilities of these things, you might want to uh, keeping these probabilities might be given to you. With that probabilities, you have to compute this. I think those example. mm, I
Sir,
have a
is
few
this topic
numerical examples.
important?
Yes. Beam search is important because actually beam search is used in most of the language models today. Uh, because if you are just choosing the higher uh, thing at every time step, you might not actually get the overall highest probability sentence, right? So this is an example that I gave, right? So this is the probability distribution at one time step, correct? So assume you are choosing this. So the next time step probability is this, okay? And the next time step probability is something different. Always choosing this one might not give you a uh, overall probability of highest thing. That is also there. So depending upon that, you might want to explore a set of top 10 candidates uh, accordingly. The top 10 candidates you might want to uh, store to get the overall highest probable sentence. It is kind of searching along the lines of that. Okay. So when you use this word as the input, your output for the next time step might be this. But when you use uh, this as the input, let's say this would be a very extreme example. Assume your probability distribution is like this. If you use this as the input, your next time step might have something like, um, let's say, if you are using this one, first one as the input, then if you're choosing this, your output might be something like point two, point two, point two, point two, right? But if you are using the second one as an example, this value as the input, your next word predictions might be something like uh, this, maybe something like this. Mm, I think they're okay. Yes. So if you are using this particular word and you are passing it in auto-regressive mode to predict the next word, if your predictions are like this, now your overall prediction will be top of this and the highest of this, which will be kind of 0.06, zero 0.6, right?
Point zero.
0.06. Yes, 0.06. But here, if you are using this one, your highest probability is 0.08, which is actually higher, right? If you are using this one as the first word and predicting the next word, the probability distribution looks like this. So this is actually having a higher probability than the previous two words, right? These two words have a higher probability than this and this word. So we might not know which set of values might give a higher probability. So we kind of tend to choose the top A some to ensure that we kind of get some good values. Okay. So beam search is also very commonly used uh, in the regressive models when you predict next word. Because the prediction of the next word, how do you predict next word? By using the probability distribution over the previous words. So the word that you choose might affect the probability distribution of next word. So to have some uh, search over there, we cannot always search the full all the k values we cannot search. It will be branching indefinitely. So we'll choose some n values and do that. That's how this beam search. Usually, increasing the beam size tend to give you some high probable sentence, some good sentences out. But sometimes it might not give. So, like computationally expensive, right? Having to have this many beams. So basically, if you have two beams, you have to pass this also as the input, this also as the input, and predict the output. So having it's computationally expensive, so we do something appropriately according to our needs. You can go with one if you beam size is one, it's basically greedy search. The always choosing the highest probable word and going on. Okay. Always choosing the highest probable word might not give you the highest probable sentence, and that's what I kind of demonstrated. So that's why beam search is necessary. So actually, it is an important topic in that sense. Okay. Okay. Oh,
Sir, regarding blue score, can you go to that examples page?
yes.
Here in the apply the brevity penalty, he has not used the minimum function.
This one. This
Yeah.
is minimum. What is minimum doing here? It is just a guard to avoid negative values. Sorry. No, no. Avoid minimum of this. No, no.
So in the example, it is
Okay.
some negative value
Okay.
came, so he has directly taken
Okay.
the.
Okay. Okay. Let me check. Let me check. So here the brevity penalty uh,
So
is it
one
this
might.
value itself?
Yeah.
Mm, okay. The min is the issue, right?
Yeah, that's what
Mm,
we discussed, and he said he will confirm before exam whether to use how to apply this formula.
I think here this shouldn't be min. This should be actually max, I guess. Let me check this.
Sir, actually the fraction is causing the error. If the denominator becomes lesser than the numerator, then it will negative.
Yeah, that's why I think. Okay, let me fix this. Uh, Ability penalty. Let me check for themselves. Ability penalty is the issue right now. Mm, Here the minimum is not mentioned. I think he took it from this. Uh, Example was taken from the other source, right? No. Let's see. I think this course should be there in here also. Here, let's go over to the let's see. You need to sign in. Let's PP. Yes, the one. Uh, yes. Okay. So this is min of this minus zero only. In that case, mm, okay. So when do you get negative value here? Uh, if R is greater than C. So can R be greater than C in this case? So, okay. So R cannot be actually greater than C, right? What is the C? Sorry, wait a minute. R is the actual thing. C is the predicted thing. Uh, okay, if R is greater, R is the actual and C is the predicted. So the predicted, if this is greater than the actual, this will be less. Right? If this is greater than the predicted, this will be greater than 1. This is negative. It goes negative. Okay. It is defined like this. So this 1 if C is greater than R. Yeah. Okay. Actually, this is coming from this only. So this exponential is there, right? This exponential is there, right? That's what is causing this 1 to become 0 here. This is e power 0. So you rewrite this as e power 0, and this part becomes uh, e power 0. And when you take the log out, it is either this or this. So if C is greater than R, which means if C is greater than R, it becomes 1. So it becomes 0 in that case. If uh, C is greater than R. If C is greater than R, yes. Yes, if C is greater than R, it becomes 0 here. Does it make sense? Let's take this one. So this is actually correct only. So in that case, this is this uh, R, R, right? This is the R. Yes, there is R, the original thing, and this is the predicted thing. So in that case, if this prediction is more than the if the prediction is more than the label, uh, R if the if the yeah if the prediction is this is the prediction. Yeah. This is the prediction is less than or equal to the R. If it is less than, then we'll take this as the thing. So if this is less, prediction is less, which means this will be a um, positive value, and we'll take okay.
So if prediction is less,
Now
that will be a negative value.
yes, that's the idea. So basically the idea is if prediction is less, so brevity means you are not predicting the full sentence kind of thing, right? If the prediction is less, you need a penalty to reduce the score. Okay, you need to reduce the score somehow. Here you see this will be negative, right? But exponential is there, right? So that will actually make it positive. So we have to see the exponential also, right? Here, if the prediction is more, then what will happen? This will be negative. Sorry, if the prediction is more, the minimum will be 0,
0.
which means
E
we
power
don't. This
be
whole
1.
thing will become 1,
Yeah.
so we don't have a brevity penalty. So if we have prediction is equal to the length label or more than the length of the label, we don't have a brevity penalty
Yeah.
because this will become 0 and
Yeah.
the exponential will become 1.
Yeah.
So if this is less, then we'll have some negative value over here, which will be covered by the exponential function. So here in this case, this will be some negative 2, right? So exponential will make it positive. X power of minus 2. Exponential will always give you the positive value, right?
Yeah, okay.
So that's why. So these are the two ways of defining it. So here, yes. So here it is defined like this: e power this one and e power 0. That's what the 0 here comes from. The log in the log thing, you have the 0 here because this is e power 0. So what it says is that if the prediction, if you are predicting more than the actual length, no penalty. If you're predicting less than the actual length, you have some penalty, right?
Yeah, okay, okay. Clear.
Anything else that you need to look into? I think that's all things are covered. So take a look at how you form the vocabulary and things like that. And uh, other than that, pretty much this one only. Mathematical things, you need to know about how weight matrices work. Understand the distinction between the PyTorch RNN and the RNN defined here because of the output matrices, and whatever is the Y defined as output here is not the same as output that is coming out of the RNN layer. Okay, that distinction should be there if you understand. Those are the important things. Anything else? Also, take a look at these questions once. That will give you an idea. Okay, then. Then you can stop with this. Thank you, everyone.
Thank you, sir.
Thank you, sir.